Okay, good morning everyone. This is Dr. Schultz, and this morning I'm going to deliver a screencast lesson. The lesson is about power and Watt's law. This is learning target 8.3, and just a couple of words here. The expectation is that as I go through these slides that you guys will be taking notes and writing down the stuff that's on here. So I would expect at this point that you've got your notebooks out and you are ready to go. Let's just kind of take a look at the learning target first. This is 8.3, and we want to calculate the power that's dissipated by a resistor when the voltage, the current, and or the resistance are known. You also want to relate the power to the energy that's transformed in a circuit, and you want to perform simple cost calculations for appliances, etc., and develop an appreciation for how much it costs to power typical homes and schools. So we're going to be talking about power, and Watt's law is very much like Ohm's law that we talked about yesterday. Okay, so let's get started. So the first thing that we have to remember is that let's go back to the first semester and recall that power was defined as the rate at which work is done. And back in the fall, we talked about power a little bit in the context of mechanical systems. So if a force was doing work on a mechanical system, you would say that power would be the rate at which the work was being done. It's how fast work was being done. When we talk about electricity, we're going to be talking about the rate at which energy is converted into other forms. So what we'll do is we're going to start with our definition of power. Power is defined as work over time, but it can also be defined as the rate of energy change over time. And so you've got the formulas there. Either one are correct. And the unit that we used for power, the unit that we used for power was the watt. And a watt is defined as 1 joule per second. So hopefully this sounds familiar. Now the thing that we'll really be interested in is we'll usually want to figure out how much work is done or how much energy is converted when we're talking about electrical circuits. And so what we do is we rearrange that formula that you have up above. And we're going to rearrange it to solve for work or energy converted, which means we're going to take power and multiply it by time. So if you rearrange that formula using the standard units, you find that 1 joule of energy corresponds to what we call 1 watt second. Okay? Now 1 watt second is read exactly like that. It is not 1 watt per second, but it's 1 watt times a second. And that should make sense because if you multiply power times time, you should be getting energy. Now, one of the things about this unit is that a joule, as we already know, is a very small unit of energy. So it is oftentimes useful to talk about larger units, especially when you're measuring the energy that you would use in your house. The unit that the power company uses for energy is called a kilowatt hour. And a kilowatt hour is defined as 1 kilowatt times 1 hour. In other words, if you used 1 kilowatt of power for an entire hour, that would correspond to a certain amount of energy. So the amount of energy that it corresponds to would be 1,000 watts multiplied by 3,600 seconds, the number of seconds in 1 hour. And this corresponds to a lot of joules. 3.6 million joules would correspond to 1 kilowatt hour. This is a much larger unit of energy, and it is more useful for everyday energy usage at home, school, etc. So from now on, you can think about the joule and the kilowatt hour as both being units to measure energy, but the kilowatt hour is about 3.6 million times larger. Now let's talk a little bit about the cost of power. First of all, you or your parents do not pay the electric company for power. What you do pay for is the total amount of energy that's used in your home. And here's an analogy to think about this. Many of you are now driving, and when you go to the gas station, when you pay the gas station, what you're paying for are the number of gallons of gasoline that you buy. You're not paying for how fast you pump them. Okay, that would be kind of silly. you're actually just charged for, say, buying 15 gallons of gas, not the fact that it took you 3 minutes to put them into your tank or it took you 2 minutes to put them in. So it's very similar with power and energy. Power is how fast, and energy is how much, and you ultimately are paid for how much. Now, in this, the state of Illinois, we pay about 10 cents for every single kilowatt hour of energy used in our homes. When I say we, I mean probably your parents, in other words, homeowners. The rate that our school pays is a little bit less. It's closer to 6 or 7 cents for every kilowatt hour because we get a discount as an educational institution. But at home, your parents are paying about 10 cents for a kilowatt hour. Now, that doesn't sound like much, but in some of the problems that you'll be solving, you're going to see that it adds up, especially if you leave appliances and things on. So I took a copy of my electric bill from home. This is a ComEd bill, and this is a monthly bill. And you know, there's a lot of information on here, and I'll draw your attention to kind of this this part in the lower right-hand corner. These are the charges that I pay for every month. Now, in my home, during this particular month, we used about 470 kilowatt hours of energy. And my home is fairly small. There are 4 people that live in it. And if you live in a larger home, or if you have more brothers and sisters, you're probably going to be paying more than 470 kilowatt hours. If you live in an apartment and you have a small family, you might be paying less. Now, ComEd is kind of tricky about this. What they do is they basically split up that 10 cents per kilowatt hour, and they charge it according to different items. So if you look here, you'll see that there are about 6 different numbers that add up. And these numbers add up to about 10 cents per kilowatt hour if you were to go through and do this. So for example, the very first one there, I don't know if you can read this, it's about $0.06968 per kilowatt hour. So that's about 6.9 cents, or about 7 cents. And that's what they charge, what they call the electrical supply charge. And then they break this down, and they have other names for different things. But at the end of the day, when you add those up, it's about 10 cents per kilowatt hour. Now, if you look at the column over here on the right, and you do the math, they end up charging me $73 overall. If you did the math on this, it turns out only about $45 comes from the 10 cents per kilowatt hour. There are some other items here which are added on as flat fees. For example, there's a customer charge of $14. There's a purchased electricity adjustment of $2.35. And so at the end of the day, I'm actually paying $73. So there are some additional fees that are added on here. So let's do a cost of power example problem. For example, let's say, how much does it cost to operate a 1500 watt space heater for 4 hours? The way that I'd like you to set this up is to list the given information and to identify what it is that you need to find. So what we're given here is that the power is equal to 1.5 kilowatts. So I've converted the 1500 into kilowatts. And the time is 4 hours. And notice I'm not converting the hours into seconds, and I'm going to keep kilowatts as kilowatts because I'm anticipating multiplying these two things together. Now, to find the cost of energy, I have to recognize that it's about 10 cents for 1 kilowatt hour. So to solve this, what I do is I'm going to multiply power times time, and I would have 1.5 kilowatts times 4 hours. This gives me 6 kilowatt hours. Again, it's not kilowatts per hour, but it's kilowatt hours. And knowing that it costs 10 cents for one of those kilowatt hours, I can see right away that I'm going to pay about 60 cents. Okay, so your teacher might want to just pause the screen here and give you a chance to write this down. All right. And let's finish up today with something called Watt's Law. And Watt's Law is basically, it's going to be a lot like Ohm's Law. It's a formula, and it's going to let us relate the power that is used in an electrical circuit to things like voltage, current, and resistance. Now, let's start with the definition of power. Power is equal to work divided by time. Work, as you remember from the last unit, is equal to charge times the voltage difference. And I'm just going to write that as a V here instead of a delta V. If you regroup those terms, you see that Q divided by T can be grouped together and multiplied by voltage. And the reason I did that is because we now know that charge over time is equal to current. And so Watt's law lets us calculate the power used in a circuit by multiplying the current in amps times the voltage in volts. And so 1 watt is equal to 1 amp volt. And again, it's not 1 amp per volt, but it's 1 amp volt. And this is a convenient way to find power. So what this means is that if you want to estimate the power that's used by a device, you simply need to know the current that it draws and the voltage that it operates at. As an example, if you have a device which delivers twice the current at a given voltage, you will be doubling the power. This is a great convenient formula to use on household items, since your house runs at 110 volts, and oftentimes the current is printed on the device in your home, like say a hairdryer or an electric mixer or something like that. And your instructor might want to pause here so you can finish writing this down. Okay, and let's finish up Watt's law. Watt's law is written as power equals current times voltage. I'm now going to show you 2 other ways of writing down Watt's law. One thing that you can do is that you can substitute current times resistance for voltage. In other words, use Ohm's law. And you get a form of Watt's law that looks like this. It's I squared times R. So we just did a substitution for the voltage. This formula is often used to calculate the power that is dissipated, that is turned into heat, by resistive elements. As an example, if you have a device which uses 5 amps of current, and the device has a resistance of 2 ohms, what you can do is estimate the power used by the device by squaring 5 amps and multiplying by 2 ohms. So that would be 25 times 2, that would be 50 watts. So this formula is another version. P is equal to I squared R. It's very useful. It's also a version of Watt's law. And another version of Watt's law can be obtained by substituting V divided by R for current. And hopefully you can see that V divided by R also comes from Ohm's law, except now we're plugging in and substituting for the first part of I times V. When you substitute in, you end up with the formula that power is equal to V squared divided by resistance. This formula, I will say, is used less often in physics, but it is useful when voltage and resistance are known. As an example, I will say that oftentimes it's useful to calculate the resistance of an object if you know the power that it uses and the voltage that it operates at. For example, a 60-watt light bulb that runs at 110 volts is going to have a particular resistance. You can actually work backwards and calculate the resistance by using this version of Watt's law. So you would do that by saying that 60 watts is equal to 110 volts squared divided by resistance, and the resistance here would be solved and found to be 200 ohms. Okay? So what we've done here in this particular case is we've substituted in Watt's law for power is equal to current times voltage, and I've kind of shown you 2 additional formulas that can be used to essentially calculate the same thing. Okay, so to wrap things up, what we have here for Watt's law are essentially 3 equations. These are very useful. Each equation is going to be given as power is equal to some type of a product or a quotient. What we started with was saying that power is equal to current times voltage. We also derived the formula power is equal to I squared times R, which is current squared times resistance. And we finished up with the formula power is equal to V squared divided by resistance. So I would recommend that tonight you have a look at the Physics Classroom website, look at your book. You've got some sections there on power. And in class today, you're going to be solving some problems in teams, and you'll be applying these equations. All right, so have fun, and I look forward to seeing you tomorrow. Bye-bye.